In this video, I'd like to continue our exploration of hypothesis testing in a process improvement environment. And the specific learning objectives for, for this video include working with some applied data and using that data to set up a hypothesis test using Microsoft Excel. We'll perform the test and then interpret what the results from that test mean. And then at the end, I want to make sure that I provide you with a little summary sheet of tips associated with performing hypothesis tests. So let's jump in and take a look at the data. I'm in the data file that we use in our Lean Six Sigma data analysis program. The file is called hypothesis tests, appropriately named, I guess. And I have also included worksheet tabs that have different types of data for the specific different types of hypothesis tests available. And if you're unfamiliar with some of these names like t-tests and ANOVA, um, I I encourage you to take a look at earlier hypothesis test videos. In any case, we could also rely on statistical packages, wizards, to help us to determine the appropriate hypothesis test. Or, we can go old school and take a look at some of the decision maps or flowcharts that are used to help determine appropriate hypothesis test. But I've got the worksheets set up that tell you exactly which test to use if you're still uncertain. Okay, so in this first example, I'd like to take a look at these two columns. This is a couple of samples from machine performance data. The output is how deep the hole was cut or drilled for a particular drill press. Okay, so the question is, between the two machines, is there a difference? Like, is this maybe machine one is before, machine two is a future state implementation, maybe different drill bits, maybe different technology, different SOPs, or maybe this is current state and we have one line that uses this machine and another line that uses this machine, and we're wondering, is there a difference between the two? Are they both operating at the same level of performance? Before I run a hypothesis test, I take a look at the data and I try to make a determination, do I even need a hypothesis test? Are there other ways to show whether or not there is a change between the two data sets? And honestly, I think that there is. Even with a small sample size like the one we've got right here, there are a lot of tools that we've explored that I think maybe do as good, if not a better job of helping to understand if there's a change or not. Like, I'm just going to use a real simple one. Let's box whisker this thing. I'll take these two data sets. I will go up to the QI macros menu, choose box, dot, and scatter plot, and we'll create some box whisker diagrams and group this data by column. And I can already see that, well, there appears to be a difference between the two center lines here. Remember, in a box whisker diagrams, this is the median. We separate data into quartiles: first quartile, second, third, and fourth. And so the delineator here between green and gray, that's the median. But it does take a look that it does look like the averages are a little bit different. The amount of spread for most of the data is a little bit different. Looks like machine 2 has a little bit more spread. However, machine 1 does have what appears to be an outlier here, more than 1.5 times the interquartile range is where this data point was. So, you know, first glance, using box whisker, I'd probably say it looks like the data sets are different. Let's see what a hypothesis test says on this. So I'll go back to the original data. We'll highlight our data, and I'm going to go up to the QI macros menu to, now there's a couple of ways I could do this. I could choose the stat wizard and have it determine which test is most appropriate based upon the data and the things that we're looking at. Or if I felt like I needed to, I could go to statistical tools and I could choose the specific test that I wanted. I think what I'm going to do is I'm just going to run the stat wizard and have the software calculate it for me, or have the software determine it for me. Um, and sure enough, it says the variances are about the same, and it looks like the means might be different. And here are the results. And I'm going to zoom in a little bit so that you can see what the outputs are. Notice here's the original data. Um, and then we have a number of descriptive statistics here. In a moment, we'll try to interpret those. We have the box whisker diagram though too. You know, one of the nice things about the QI macros statistical testing is that it typically includes some visuals, whether it's a histogram or box whisker diagrams, to help with the analysis. But we know if after we have identified the data, chose the appropriate type, and run the test, what we're looking for is a statistic called the p-value. And what we want to see are p-values that are less than the 1 minus the confidence level that we're looking for. In most cases, the statistical tests are run at 95% confidence, just like this one was. And so I'm looking for the p-value, and I see 1 and 2-tailed p-values. I always choose the 2-tailed because it's a little bit more rigorous. Hey, take a look at it. We've got a p-value that is less than 0.05. So that means we can reject the null hypothesis. Earlier videos describe what rejecting the null hypothesis means, but our null hypothesis is set up so that the null hypothesis equals the no change claim. We're starting out with the assumption that these two data sets are the same, that there is no difference between the thing that we're testing for, which is in this case the mean, and we're assuming that they're the same. The software with its low p-value says reject the null hypothesis, so that means say no to the no change claim. That means that there was a change. There's a difference between the test statistics that we are comparing and or that we're trying to understand if there's a difference for, and that is in this case for this t-test, the mean. We've got the average at 23 and the other one at 20. We saw that before earlier in the box whisker diagram. We said, I think there's a difference. And now at the 95% confidence level, this test says that yes, there is a difference. Whew, there you go. That's how we would set up and run a hypothesis test when we're taking a look at two samples of data. Let's take a quick look at another type of test where instead of looking at two samples, we're looking at three. I've got, in this case, I've got data from a catapult exercise in which we've got three individuals that launched projectiles. We're measuring their distance. It's continuous data. And I'd like to know, is there a difference between their means? When I'm dealing with three or more data sets and I want to compare means and find out if there is a change, the tool I would use is something called ANOVA analysis of variance. To run the test, I go and highlight the data. Actually, to run the test, the first question is, do we need the test? I'd argue we could probably find out if there's a difference in mean using other techniques. Box whisker, histogramming, comparing other descriptive statistics like mean and standard deviation. We could take a look at performance capability metrics. There's a variety of things that we could do, but let's say we've decided we want to run a hypothesis test. Here's how it would work. Highlight the data, go to QI macros. I could choose the stat wizard, or I could go in here and choose the appropriate ANOVA test. I'm just going to let the stat wizard work its magic for me. The data is normal. Looks like the variance is about the same. And now let's take a look at what the results say. I'm going to zoom in, and we've got their averages right here, 105, 102, and 106. We've got their box whisker diagrams, and I would say that there is a wide amount of difference between the variation in Mike and Wendy. But ANOVA is comparing means or central tendency, and I know that a box whisker diagram is medians, not means, but frequently the means and medians are pretty darn close to each other, and just this simple visual shows that it looks like the averages are pretty close to each other. I would actually say I don't think there's a change. There may be differences, but not with the mean. Let's see what the hypothesis test says. So in this case, we've got things like average here. We've got the square of the standard deviation here. And I'm looking and scanning for a p-value. And here it is. Here's the p-value. The p-value is 0.691. We're looking for p-values that are less than 0.05. So it's greater than 0.05. We cannot reject the null hypothesis. We have to accept the null hypothesis. Remember, the null hypothesis is that there is no difference, no change, and the hypothesis test is saying we're going to accept that there's no change. They are the same. And so this test says their means look to be about the same at a confidence level of 95% or higher. One more real quick example here for you. Sometimes you're comparing a sample, like in this example, bulb life in hours, to a spec limit or a threshold that you're trying to meet or exceed. And so I'm looking at, I want to see, do these bulb life hours, is the average for these bulb life hours, is it at the 2,500 hour mark, which is what our threshold is, or our promise to customers is. Let's see what our hypothesis test says. Is this mean the same as 2,500? So here's what I'll do. I'll highlight the data in Excel. I'll go to QI macros, run the stat wizard. Here's what we find. Here's the here's the value that we're doing for comparison. Here's what the mean was. But now we're looking for a p-value. I typically use two-sided, a little bit more rigorous, and boy, that's a really, really small number. Remember, we're looking for numbers that are less than 0.05. So if it's less than 0.05, we reject the null hypothesis. The test, the mean is different than the test value that we're comparing against. So 3 different types of tests. Next, what we'll do is take a look at a quick summary sheet to help you with running tests. All right, here's a quick little summary sheet that helps you anytime you're thinking about doing hypothesis testing. I'm just going to walk through this with you. So the first thing that I always do is I check to make sure, is the test really needed? Can we show that there's a change using other techniques that people understand better? Frequently, I don't need to run a hypothesis test. But if I do, I make a claim that the data sets are the same. We call that the null hypothesis. And then we want to show with some high level of confidence that the claim can't happen, that we want to reject it. It's usually at 95%. Then we determine the hypothesis test type. This is going to depend upon the type of data and the test statistics that we're comparing. T-test, ANOVA, Z-tests, all examples of this. Then we have the software calculate a p-value. After the p-value is calculated, we then compare that number to 1 minus the confidence level. In most cases, that's 0.05. And then the bottom line is if your p-value is less than 0.05, that means that you can reject the null hypothesis, which means that the data sets are different. When we see less than 0.05, we are excited. We've shown that there is a change. There is one exception to the general rule. It seems like there's always an exception to every rule, and that is the Anderson-Darling test for normality. In that case, we're actually looking for a p-value greater than 0.05, but almost every other test, it's the other way around. P-value is less than 0.05. There's your summary sheet. Good luck with hypothesis testing.